Another way to hedge an interest rate is through what's called a caplet. Now, a caplet has a design that's similar to a forward rate agreement, but it's an option. And that means that it only provides a payment to the long position when the formula is desirable. It never costs the long position money, so it's truly an option. And so what a caplet does is it replaces, in the FRA formula, it replaces today's forward rate with a fixed rate K, sometimes called the caplet rate. And secondly, it makes the FRA formula into an option, so that the payment is the greater of 0 and the payment. So you can think of it as 1/2 of an FRA, the favorable half, but where the strike is defined in terms of this constant KR rather than in terms of today's forward rate. So this is truly an option, a caplet. Apparently, if you go back to my earlier example, this could also be used as a hedge for that loan situation. And this is a hedge that has the advantage that if the prevailing rate is lower in the future, I can do my borrowing at that lower rate. Whereas if the borrowing rate is higher, this caplet will reduce my borrowing rate to the caplet rate of K. It has the disadvantage, of course, that you will have to pay for this option. A forward rate agreement, like a futures contract, has no upfront cost typically because you are recognizing and accepting that your payment may be positive or negative, and the contract is priced so that the value of the positive and negatives offset. Here, you're only getting a positive payment. You must pay for that. So it's a different way to hedge our borrowing position, one that costs us money, but gives us the benefit that if prevailing rates are low in the future, we can take advantage of that. So let's do a little bit of algebra. If we convert that payment at time t plus s, that option payment, to time t, we would do that by way of a present value at the prevailing rate, same mathematics we saw a minute ago with the FRA. And notice that when we do this, we have that this cap, or caplet, a single payment's called a caplet. This caplet, if I convert its payment to time t instead of time t plus s, this caplet is equivalent to a fixed number of put options on a zero coupon bond. If you look at this formula, maximum, this is a put option, and this is a zero coupon bond, P of t, t plus s. It's the price of a zero coupon bond. This is a put option on a S period zero coupon bond with a strike price of 1 over 1 plus the cap rate. So what we've done is to convert a call on rates, which is what a cap is. It's a call on rates. And we've converted it into a fixed number of puts on zero coupon bonds. Well, the black formula tells us how to price calls on zero coupon bonds. So with put call parity, which we'll now look at, we should be able to convert that to a price of a put on a zero coupon bond, and through formula 2436 we will then have the price of a caplet. Now, put call parity in the general setting was in fact discussed in module 2 of chapter 12, and that was the generalized put call parity related to prepaid forward prices. And it says that if I have a call on S with a strike of K, and I add to it the prepaid forward price of K, I get the same as a put on S and the value of a prepaid forward on S. So this was the generalized put call parity that related puts and calls to prepaid forward values. Another way of writing this then is in terms of the put, and that's what we desire, right? Because the cap let was equal to a fixed number of these puts. So what we've derived is that we can price the put on that zero coupon bond by using Black's call on that zero plus some adjustments. And let's look at what that would be in a little more detail.